Last time we talked about parametric curves and we had definitions. So now here you have some exercises that you actually got to put on the computer and actually take a look at those curves. Those problems that you saw were problems taken straight from your homework. I don't know, has anybody started with the homework yet? If you've seen it, then those problems just came directly from the homework. The homework is actually a matching problem where you have a graph and then you have those equations and you try to match it. So um, here I try to make it so that you actually have to graph it and find it yourself. Just to get you used to using the computers, using Desmos, and using some sort of graphing program that would be useful. Are there any questions about the logistics for the classes as you guys are going through the work? Yes. No, I don't mind. So you can work ahead if you want with WebAssign. Go as far as you need to, want to. Yeah. All right, we'll take a look at it after class. I'm hoping that once you get into WebAssign, you should be able to get in. I had some issues with some other students. Yeah, I mean, you guys used WebAssign last time, right, with your last class? So there was an issue with a Calc 2 student who was in my Calc 1 who couldn't get into WebAssign. I don't know what's going on, but we'll take a look. All right, parametric curves. This is what we did last time. So this is like the pre-calculus version of studying parametric curves. We learn about it, we graph it, we can talk about it. We write the equations and stuff like that. And so now we're going to do some calculus on the parametric curves. So let's take a look at some tangent lines. So for this section, we're in section 10.2. We're going to look for tangent lines. We're going to look for areas within some parametric curves, arc lengths, and stuff like that. So stuff that we did in Calc 1 and 2. So if you have a parametric set of parametric equations, x and y, your dy dx is actually given by dy dt divided by dx dt. So it's really just taking a bunch of derivatives of things. We could take a look at the simple example that we did where we had circles. X equals cosine t, y equals sine t. And so if we want to take a look at the derivative at a particular point or at any random point, then we can say dx dt. What's the derivative of cosine again? Negative sine t, dy dt equals cosine t. And so the derivative is just dy dx equals dy dt over dx dt, and that is cosine t divided by negative sine t. So this is the derivative at any particular point. We can get specific about which point we're talking about by putting in the values, the value in for t. So the derivative is just a derivative. What is this equal to? Any of that's like tangent or cotangent or something? Negative cotangent. Anyways, I'd like to follow these things up with some graphs. And we'll let's pick a random value for t. So let's say line tangent at t equals pi over 4. Okay, so let's say randomly pick pi over 4. Just so you know, and because this is our standard circle thing, um, cosine pi over 4 sine pi over 4 is that point over here. So we would expect the slope of this to be -1, right? So let's find that. So the slope it's going to be given by the derivative, and then we have to evaluate this because if we don't evaluate it, it's just a general function. And so we saw that in calculus 1 that if you want to find equations of the line, you actually have to evaluate it at a specific point. And so if we put pi over 4 in there, we got cosine of pi over 4 divided by negative sine of pi over 4. I think they were both equal to √2 over 2. And then we get that. Okay? So that's our derivative, and if we want to find the equation of a line, then this is where we go. Are there any questions? So since we have Desmos out, we can actually just graph this. Our derivative, y minus what's the y value? Sine, right? Is equal to the slope. The slope we got was cosine divided by negative sine. And x minus, what's the x value? Cosine. There you go. Pretty cool, huh? You know, something really cool? I wrote it like this. Math people in general like to do things in symbols and without actually evaluating it, just so in case we're interested in making a parameter out of this. Let's change the generic point. It's not generic, but let's change the specific point pi over 4 into a generic point. Let's call it A. And then every time we move A around, actually we can do this A also. Now it's cool. Okay. So the idea is to get the derivative, and the derivative is just dy dx or dy dt divided by dx dt. And then you put in those values. All right, that's fun. So you would think that since this is the derivative, the second derivative would just be dy, the second derivative of y divided by the second derivative of x. Unfortunately, it doesn't work like that. So let me put something that's incorrect here and then mark it as wrong, incorrect. So d squared y over dx squared seems like it would be equal to d squared y divided by dt squared divided by d squared x divided by dt squared, right? That's just y double prime divided by x double prime. Are you guys writing this down? If you are writing it down, take out your red pen and say this is bad. It's not. That's not it. Doesn't work like that. So let's figure out what to do. Turns out that the second derivative, whoops. So slightly more complicated. The second derivative is really the derivative of the first derivative, right? And the first derivative can be expressed as a function of t, but you're taking the derivative with respect to x. At least that's what dy dx, ddx is the second derivative with respect to x. So remember ddx, the second derivative with respect to x describes the concavity. So if we want to somehow describe the concavity of this parametric curve with respect to x, then it's done a little bit differently. So it turns out that the derivative with respect to x of dy dx is the derivative of y with respect to x with respect to t divided by the derivative of x with respect to t. So those derivatives, Leibniz notation is deceiving in that it might look like it's simple. We just do the derivative of the top and the bottom, but like the quotient rule, it's a little bit different. So let's see how this is going to work. We probably should use a different function because we're just going to be playing around with sines and cosines. So let's use a different function. Let's find the derivative, the first and second derivatives of this thing at t is equal to 4. And then we'll see what kind of graphs we can come out with. So first, the first derivative, looks like we're going to say d, I want this in red, dy dx. So we want y prime divided by x prime. So the derivative of y is what? 2t minus 2. And then the derivative of x is so that's the first derivative. And if we care to evaluate it, t is equal to 4, the slope at that point is going to be, put 4 in there. 8 minus 2 is 6. 4 in there. Oh, fourth, so 24. Is that right? Okay, so that's your derivative. Now, if we want the second derivative, what we need to do is we need to take the derivative of this divided by the derivative of x, the original x. So it'd probably be worthwhile simplifying. I don't usually care about simplifying derivative, except when you do second derivatives, then it might be better to work with a simpler derivative, first derivative. So let's rewrite dy dx as, say, 4, because they're reciprocal, right? So it become 4t to the first plus t to the 1/2, t to the 2/3 minus 4t to the 1/2. Does that look okay? So this would be easy to take the derivative of now because it's in a couple of pieces. You don't have to do chain rule, product rules, or quotient rules, or anything like that. So we want the derivative of this, let's say d dt of dy dx. So we want the derivative of this thing with respect to t. So that is 6t to the 1/2 minus 2t to the negative 1/2. I get my constants there. So that will be my numerator. And then I'll just use the same denominator over here. In fact, I could probably write it as 1/2 t to the negative 1/2 or something. So that's my dx dt, right? And so my I'll put those together. D squared y over dx squared is going to be, this thing is a numerator. 6t to the 1/2 minus 2t to the negative 1/2. And let's divide that by 1/2 t to the negative 1/2, and then do the simplification that you can or want to do at this point. Is that right? Something wrong? So this looks like it's dt ddt of dy dx. That's what this is. And then this came from the x prime, which is dx dt, right? That simplify if we want. Let's say let's simplify, because let's actually check it to make sure that we got it correct. How will we simplify this? So 12 t minus 4. Just 4? Oh, that's it? Wow, that's simple. This is good. This is right. All right, so this is their derivative, or second derivative. And the second derivative, if we care to put in the value of t is equal to 4. 48 minus 44. Those are big numbers. Okay. Any questions? How can we see this in the graph? You guys remember your calculus? Oh yeah, we're in calculus right now. Do you guys remember your calc 2? Second derivative, first derivative? What? It's acceleration. It's concavity also. Yeah. It looks like this should be concave up, right? Let's draw the graph. That's root and t squared minus 2t. All right, let's see if we can draw it. Would Desmos graph it automatically, or we have to type it in? We have to type it in. Square root of t squared minus. We want to include 4 here for sure, so what if we go to 5? Where are we when t is equal to 4? or up here, right? Looks like it's concave up. Let's draw that line. Y minus, what was it, 8? Y minus 8 is equal to, what was the slope again? Remember? 24, yeah, for the first derivative. So that's 24 times x minus 4. Whoops. Oh, 2, yeah. I used t. There he goes. You know what to do if you can, it's hard to see this. You know, you just flatten it a little bit. So let's take a closer look. I think if we flatten the y-axis, just let the y go from 5 to 10. Whoa, what happened? What did I press? This one? Oh, thanks. Is that what I wanted? What?
If you have a touch screen, you can just use your fingers to
Oh,
squish that.
jeez.
Try putting your fingers on the y-axis and just squeeze it.
Mm-hmm. No.
Oh, here you go. It was kind of working. Yeah, it works for a second. No, you don't want to. Yeah.
What?
It got wider.
Is that good?
No.
I wanted to do the opposite. Oh, crap. All right, so I think I want this. Let's go from 0 to 5. And let's go from something like that. So anyways, do you remember Taylor polynomials? Just for fun, let's do this. So just for fun, let's do Taylor polynomials real quick. If you guys are going to go in differential equations, eventually you'll need to know your Taylor polynomials. Do you need to know it here? Nah. Just for fun. So Taylor polynomial says that your function can be approximately equal to the function evaluated at the point plus the derivative. So if we stop here, this is essentially the tangent line. The f of a is like the y value. You bring that over to the other side. So it's like y minus y1 is equal to the slope, the derivative, times x minus x1. So that's kind of like the first derivative if we stop here. Now we tack on the second derivative. There's 1 over 2 factorial, which is really just 1/2. As derivative evaluated at that point, then x minus a quantity squared. So if we set this up, our y value, we found that using Desmos, but our y value turns out to be this is an extra equal sign. What is it, 8 or something like that? And then this was 24. X minus, now this is 2, right? Not 4. Plus 1/2, and then here we have a 44, and then x minus 2 quantity squared. So if we graph this, we should see You know, the second order tail of polynomial is really like a tangent parabola. Did you get? Yeah. Let me plot this point and let me plot this graph and see how it looks like compared to the rest of the graph. So y equals 8 plus 24 times x minus 2 plus 1/2 times 44 times x minus 2 quantity squared. So you can see, compared to where the graph is, that doesn't help. Compared to where the graph is, you can see where the parabola is like the best tangent parabola approximation to the curve. Just like the tangent line is the best linear approximation, the second degree polynomial is the best approximation. So it looks like our 44 for our second derivative was fairly accurate. Okay, just a good way to view it. All right, cool. Let's take a picture of this and put it with our notes. Whoa. Oh, it's in our notes. I'll fix it later. All right, so that's the second derivative. What else do we need to do? Let's take a look at areas. So I'm not deriving a lot of these formulas. I'm just taking it from the book, and then all these come directly from the textbook. And then I'm just showing you and kind of doing some sort of weak justification for why these formulas are true. So this is the area between the curve and the x-axis. So the general formula is the integral from a to b of f of x dx. And so if we want to retranslate that to something in terms of t, f of x is really the y value. And then the dx really is a differential if your x is a function of t is just x prime dt. So those are the components that you have from your derivatives. And your limits, just instead of going from x values, you would take them as t values. Okay, so we can find areas under the curve. I don't know if this would be the example that we had was a good example. Let's see if we can come up with another one. Oh, this is to the y-axis. So this is like the problem that we did, except it's sideways. So there are things that you probably want to do, like graph this, if you're able to graph it, just to get an idea of what it looks like, or you could let's try to do it without graphing first. So the area enclosed by the curve and the y-axis seems like this is going to intersect the y-axis, and then what? So we probably need some idea of where this thing is. So it might help if we plotted a couple of points. And this is, it's not the sine and cosine, so this might be one of those things where we want to at least put in 0 and 1 and see how it might look like. So I'm going to, I think I made fun of this last time when I said you don't have to make tables, but let's make a table. When t is equal to 0, you put into the x, you get 0. You put into the y, you get 0. So you're at 0, 0. So we know that the intersection is going to be, there's an intersection at 0, 0. Let's try to put 1 in. I put 1 in here. We get 1 minus 2, so that's negative 1. And then you put 1 in here, you get 1. So -1, comma, +1. So we're over here somewhere. And let's try to put 2 in. So it looks like it's moving this way, right? Maybe. Again, we'll use the graph to confirm this. If we put 2 in there, we're going to get 4 minus 4, that's 0. So that's going to bring me back to 0. So this is going to give me a really good idea that it's probably going to come back this way. Square root of 2, whatever the square root of 2 is, like 1.4 or something like that. 1.4 something. So we're up here, not more than 2. And then I'm assuming this is so taking some sort of parabolic turn, so it's probably going to go on forever. So I probably want this little area here. And if you remember back in calculus, if you look at it, turn your head sideways, it's kind of below the y-axis if your head is turned sideways. To the right. Yeah.
So what function is above the curve or the y-axis?
Well, they say the curve enclosed by the curve and the y-axis. So this must be the curve, the area that we're looking for, right? So we can try to figure out what that curve is, and then write it as a function. Y is a function of x, or x is a function of y. But let's actually use the derivative. So let's say we know what this curve is, or x is a function of y. Then, or let's write g. So this conceivably this could be like y to the 4th plus something or other. Then our integral, our area, is going to be the integral of these two intersections, whatever this is. I know this is 0. Oh, this is square root of 2. So 0 to square root of 2 of whatever this function is, dy. I don't know if this is quite correct. What's wrong with this? Turn your head sideways. What? It should be negative. Because it's below the x-axis. Again, if you look at it sideways, it's below. Unless you want to talk right, left, right? That's positive, left is negative. Right? So the area is on the left side, so it's negative. So you got to do the switch in the order. So the area should be negative. If I don't put a negative there, I'll get a negative area, and then I'll just compensate. All right? So this is what we would do if we could find out what g is equal to. But we have the parametric equations, so let's just use the parametric equations. And what we're going to do is we're going to transform your x values. This is your x, by the way, right? I want that green. And this y is going to be the derivative, the differential. So this would be y prime of t dt. So that's how it's going to transform. And I think we got lucky in putting in the values of 0 and 2. So the y value of 0 is obtained when t is equal to 0. The y value of square root of 2 is obtained when t is equal to 2. Okay. Is that okay so far? All right, so looking good. Let's rewrite our area as an integral from 0 to 2 of x. So this is just t squared minus 2t by itself without having changed. And then we need x, well, we need y prime. Y prime of t is 1/2 t to the negative 1/2. And then now we have a function of t that we're integrating. Oh, let's not forget the negative sign. So let's integrate this. How do you integrate again? There's a 1/2. Let's bring the 1/2 all the way out. This is, oh, I guess let's not integrate yet because let's bring the 1/2 all the way out. And we got t. What do you do here? You add or multiply? You add the exponents. So t to the 3/2 minus 2 t to the 1/2. Right? And then you integrate. So let's throw negative 1/2 here. Integral of this, you add 1 right to the power and divide. So that's t to the 5/2 divided by 5/2. So that's multiplying by 2/5 minus 2 t to the 3/2 divided by 3/2 multiplied by 2/3. And we evaluate this from 0 to 2. So what happens? Let's put 2 and let's just put 2 in there. We have, I hate math. I mean, algebra, whatever. Negative 1/2, 2/5 times 2 to the 5/2 minus 4/3 times 2 to the 3/2. Oh, I hope this is positive. Yeah. Upper bound is 2 because we changed it from, initially it was y, and then we changed it to t. And this is your y at the upper bound. This is your t at the upper bound. So it should be 2. Somebody putting it into the calculator? Somebody will.
I got x square root over 15. So it is 0.75.
Did you say 8 squared root of 15?
Yes, over 15. Square root 2 over 15.
Oh, square root of 2 over 15? Eraser.
And the 8. We have 8 square root 2. Sorry.
Yeah, awesome. Cool. By the way, this is an interesting problem. This g of y, I said, well, who knows what g of y is? Who knows what g of y is? Let's take a look at the set of equations that they have here and see if we can write this as a relationship between x and y. So I essentially want to eliminate let's try to see if we can eliminate the parameter t. And maybe what I could do is I can square both sides of here and get t by itself. And then maybe I can put that into the x equals, oops, t squared minus 2t, but we found that t is equal to y squared. So it looks like x equals y to the fourth minus 2y squared. Interesting. Desmos. So the neat thing about Desmos is that you can, unlike your handheld graphing calculator, you can write an expression where x is equal to some function of y. At least we see what happens square root of 2. Hmm? Oh, yeah. Right? That probably means that if I were to integrate this function from 0 to square root of 2, with a negative in front of it, you should get the same answer. Let's see. Wow. Your final answer should be positive, right? So if I had a negative and an integral of y to the fourth minus 2y squared, where y goes from 0 to square root of 2, then we should get, what is it? 8 root 2 over 15. Magic. It's not magic, it's just math. Positive and everything. Okay, so it's the same answer. Is that cool? All right, so that's it for today. Next time, I don't know, something.